there's a lot of new stuff here that you might not have seen before. So what I'm going to do here is I'm going to take 2 sessions to go through this, to get through as much as we can, because there's a lot of stuff here that you might struggle with to go through by yourself. So the ICE task, I'm not going to give you guys too much work here because it covers a lot of examples in the learning unit. So as we go through, I will probably just highlight examples, and by the end, I'll make a list and tell you, okay, all these examples from the lecture notes, which I've highlighted, just do those as an ICE task. Whether I've done them already, it doesn't matter. So that will be practice for you guys, because anyway, I won't be able to get through all the examples. So there's no separate ICE task here. It's just going to be a part of the lecture notes, and I'll tell you at the end of the lecture next week what the tasks should be, and then I'll give you another week or so to submit that. Okay, so for today, don't worry about ICE tasks. So let's get started with learning unit 3, which is, first we're looking at theme 1, which is mathematical logic. Get a bit interesting because we start talking about ways in which things that we call statements interact with one another. And a statement is just usually mathematical, but for some reason here we start off by talking about statements in terms of English. Again, it doesn't matter how you talk about your statement, the rules that apply to them are still the same. So we're going to look at propositional logic to start. I'm sure that heading is somewhere. If it's not, we'll see it in the chapter. So propositional logic is we're just going to look at the way statements interact with one another. And let me clarify what I mean by statement. Is a statement is defined up here as any declarative sentence which is either true or false. So as long as you're stating something, it doesn't have to be factual, it can be incorrect, but if you're stating something, then we call that a statement, right? That's pretty vague. I hope you guys know what I mean. Like if I say the sky is blue, that's a statement. If I say the grass is green, that's a statement. And there are examples down here of what statements are, some statements, and there are examples of things that are not statements. So things that are not statements, you see things like questions and half phrases which don't mean anything. Like the second point there is the sum of 2 squares. It's not really declaring anything. It's just saying some words that doesn't really tell you anything. So if you look up where it says these are statements, we see things that are just declaring something to you. Like the second one, the moon is made of cheese, is a statement. Even though untrue, it's still a statement. Okay, so unfortunately, guys, a lot of things to memorize here. So I'm just going to point them to you and you can go back and recap as you need to. So statements, we break them up into 2 types, atomic and molecular. And these names help you to remember what they are. So atomic basically means like an atom. Okay, bad example, but it can't be broken up further. And a molecule is something which is made up of atoms. So those names tell us how to describe the statements. Atomic statements are statements which you can't break down further, and molecular statements are made up of atomic statements combined in some way. So atomic statements, again, I'll give you 2 examples. The sky is blue, the grass is green. These are 2 atomic statements. Combining these 2 to make a molecular statement will be something like the sky is blue and the grass is green. Just combining 2 atomic statements to make one molecular statement. And I use the word and to join the statements. That is something that's called a logical connective, which I think is the next section. Yes, it is. Logical connectives are just things we use to connect different statements together. Okay, so there are 5 we need to remember. And their symbols are also important. So when I say their symbols, okay, let me start by saying this. First, we talk about P and Q, which are just labels for statements. So P could be the statement, for example, the sky is blue, and you guys get the picture. Q could be the grass is green. They're just labels, right? So these labels, it doesn't matter what they are. Just remember P and Q are statements of some kind, right? So these are called, what's the word? Propositional variables, right? I'm sure the word is, there's it highlighted at the bottom. So P and Q are propositional variables. That's the first thing. Now, the logical connectives, that's where we were getting to. So the first one, the first bullet point here which has this upward like a triangle symbol between a P and Q, that represents an AND logical connective. So if we see that, the way it's read is P and Q. So for the two examples I've given for P and Q, this will be read, the sky is blue and the grass is green. Okay, and the word we need to remember here is conjunction, right? Because the word conjunction, sorry guys. Okay, sorry guys. As I was saying, yeah, the word conjunction you need to remember because you may not be told in an exam or in your assignments that we are looking at an and statement between two statements. You might be told conjunction. Look at the conjunction between P and Q, and then from that you need to know that we're talking about an and. So these highlighted words at the end are important for that. Okay. So again, guys, if you need to just interrupt me at any point, otherwise I'm just going to continue. It is just theory at this point, unfortunately. Okay, so the second one is an or. Same, it's just now this is sort of and, this is an or logical connective. So in our example, the sky is blue or the grass is green. That's what we would say. And the word that they will use to indicate to you that we're looking at an or logical connective is disjunction. Okay, so another word to remember. The next one is an implication, which means if then. So this is an important one. In fact, so important that the next section deals with only implications. Right, so I'm saying implication because this is the word they will use, implication or conditional, but implication is more common. So if you see the word implication between P and Q, it basically means if P, then Q. Right, that's how you say it, like this little part in the middle to remind us how to say that. So in our example here, this is if the sky is blue, then the grass is green, right? Doesn't really make sense in English, but that's how you would pronounce this. That's how you would word it out. It's kind of like reading another language at this point. Okay, and then this one here is if and only if. So in our example, this would be the sky is blue if and only if the grass is green. And this is called a biconditional. Okay, now the last one is a little different because this applies to only one statement. So this here is called a negation. Sorry. Somebody speaking to me. Or somebody just unmuted. Okay. Just check quickly what's happening. Am I missing something? Okay. Everyone seems fine. Okay. So as I was saying, the last statement, or rather the last logical connective, is a bit different because it only applies to one statement. So it just means not. So if I applied it to a P, it just means not P. So it just undoes P. In other words, this will be the sky is not blue, right? You could say not the sky is blue, but that sounds very Elizabethan and stuff. Depends how you want to speak, right? As long as we know what it means. It just means the sky is not blue. Just undoes the original P and gives you the opposite. Okay, and the word is negation right here. Okay, so again, I don't want to waste too much time, but that was the foundation of this, so I couldn't skip that part. Propositional variable, okay. This and this we must know as well. Binary connectives are things that join two statements. So these are the first four, and unary is one that only applies to a single one. So that's the last one, right? Can we think of some examples? We did that already. The sky is blue, the grass is green. Try connecting them using logical connectives. We've done that for all the connectives. Okay. Truth condition. So this is another fundamental thing which we have to go through. This is basically a set of rules to tell us how to determine whether a molecular statement is true based on the truth value of the original atomic statements. So, for example, we might know P is something that's true, Q is something that's false. Then we need to know how does this combined statement whether the combined statement is true or false based on the truth values of the original atomic statements. Right, so we have to look at some examples for that because that by itself is a bit abstract, what I'm saying. So anyway, the rules are up here. The rule is if you have an and you want to determine, or rather, if you have two statements combined by an and you want to determine whether the combined statement is true, then this is the rule you look at. If both P and Q are true, then the combined statement is true. Right, so all of these things have similar, not similar, but they all have rules like this that we have to follow. So let's see if we can look at some examples, might be helpful. One, let me just think. Okay, you know what? Let's actually, maybe we should look at one example for each so we know that we get what's happening here. I mean, I can just make it up and erase as I go because it will all be on the video anyway. So for and, let's say, let me just think for a moment. Let's make up an example for which it's not clear whether it's true or false, because this is what happens in these exams usually. You'll be given statements, it's not clear whether they're true or false, but you will be told. You'll be told that P is true and Q is false. So what can be ambiguous here? Let me say something like, I don't know. I'll use my own name so I don't alienate anybody. I'll say Shamik got 49% for maths. That's statement P. True or false, who knows, right? We don't know unless they tell us. Q can be, I don't know, use my own name so I don't alienate anyone. Shamik owns a, how do you spell? Shamik owns a Lamborghini, capital L. Yeah, true or false, who knows, right? Anyway, so let's suppose we're given the scenario. This will be the form of a question. Typically, you'll be given, let's say, question 1. It says, suppose P is true and Q is false. Then is, let me word that better. False. Then determine the truth value of, and then let's say 1.1 is P and Q. So what's the truth value of P and Q based on what we are given? Well, the way you evaluate this is you just look at what the individual thing for P and Q is, right? Let me change color for that. This thing will function. Right, so how do we determine whether this combined thing is true? Well, we are given information that P is true, so we know P is true, and we give that Q is false. So we know that. So based on this, and based on the rule to the left says the combined thing is true when both P and Q are true. So if both P and Q are true, then this thing is true, right? But we can see clearly here that's not the case. Both P and Q are not true, so that's why we would say this is false. If it's not true, then it must be false. Okay, so if I lose anybody at any point, just let me know. And if I'm going too slow as well, just let me know. Okay, so that's 1.1. I'm just going to do at least 2 of these so we have an idea. Let's do the second one. Will be the O. P or Q. Is that true or false? Well, we know we're given that P is true and Q is false. So based on the rule here, it says this is going to be true when P or Q or both are true. So either one, as long as one thing is true, then the entire thing is true. So P is true, that's good enough to say the entire thing is true. Right, so that's how we deal with these things. Gets a bit weird sometimes, but you guys will get used to it. Okay, there's some really good practice questions here as well. Like, let me just keep this here for a moment and think. Okay. Yeah, I don't want to go through all of them because it'll take too much of time. Here's a nice example. which deals with the next one anyway, the if-then, because this is an important one, implication here. So let's remember this rule because I'm going to have to scroll away from it now. I'll try and write it down at the bottom in a shorter form. So the implication, if P then Q is true, when P is false or Q is true, or both. Now, I'll tell you guys immediately this or both here just confuses people and it doesn't add any value to this thing. It doesn't change anything. So we don't have to even worry about that. We can ignore that if we want to. So I'm going to restate this at the bottom and then we can do the example. Okay, so what was the thing? Implication is true if, maybe I shouldn't say if, that's a dangerous word to use here, is true, is false, or Q is true. This is the thing we're interested in. All right. So now we're given an example. Consider the statement, if Bob gets a 90 on the final, then Bob will pass the class. But clearly this is an if-then statement. We can see the if, we can see the then. So the first thing we need to do is identify the statements here. Again, this is a typical type of example you will be given. So identify the statements. The first one is right here after the if. Bob gets a 90 on the final. We can call it P if we want to. Let's do that. Then Bob will pass the class. So we can call that Q. Okay. So this is now of the form if P, then Q. Right? So now we're in business, we can do stuff with it. So the question asks, under what circumstance is the statement untrue? Oh, why are they using weird words? The statement untrue, why don't we just say false? Right? Let's not confuse ourselves. Untrue is false, right? Let's just do that. So in other words, they want us to determine whether the implication is true or false based on what they tell us here in 1 to 8. So 1 to 8 should be giving us some information about whether the atomic statements are true or false. And based on that, we need to work out whether the molecular statement, this one here, is true or false. So let's firstly figure out what information we are given from 1, for example. 1 says Bob gets a 90 on the final. So I think that's telling me P is true because it's restating P exactly as it is. So it's telling me P happened, P is true. So the information I get from here is that P is true. And that's all they tell me. Now, does that help me in any way? Let's see. So if P is true, then from the implication, what we know, P is true. And the condition necessary, which is up here, for the implication to be true, is this up here. P needs to be false or Q needs to be true. So maybe I'll write in green the thing that we need to happen. We need P to be false or Q to be true. That's what we need to happen. But all we know is what's in red is that P is true. Right? So P is true doesn't meet any of the conditions above. Again, what's in green is what we need. We need P to be false or Q to be true. But that's not met here. So I'm tempted to just put an arrow here and say false. However, I don't think I can do that. Because see, we're not given any information here about Q. We don't know Q. I don't know why I wrote a 0 here. Let's just put a question mark. We don't know Q. And if Q were true, then this thing could be true. So my temptation to say false is incorrect because Q's value could change everything. So not knowing Q, this basically means I'll say not enough info. So we can't tell whether this thing is true or false based on the first one. There's just not enough information. Okay.
So make it that interchangeable. Sorry, can I interrupt you? The false and the true. Does P have to be false, or can P be true and Q be false?
Good question. No, it's not interchangeable. This is the standard. It has to stay like this.
Okay, so P is false and Q is true. Okay.
Yeah, that's it.
Thanks.
All right, you're welcome. Okay, perfect. So in fact, it makes it easier that it doesn't interchange. Yeah, it's just one set way to think about it. Okay, so let's look at 2. 2 is telling us Bob does not get a 90. Sorry.
I just want to know, why does P have to be false? I know it might be a silly question, so I just got lost there.
Sorry, I'm starting to hear you a little bit. Can you just repeat that?
Sorry about that. It's storming in PE. Now I just wanted to know, why does P have to be false? Or true for that matter. I just got lost there.
Okay, no problem. So again, I wish I could tell you why it is. It's just the standard rules here. So it's this one here that we're looking at. I just restated at the bottom. In order for the implication, if P then Q to be true, then these conditions here must be met. The condition is P false or Q true. That's just restating what's up there in the table. So I'm not sure if I could delve into why that is, because that like probably the people that formulated this, will have a better understanding. I haven't, but yeah, it's just the way it is. Just have to remember it. All right, so yeah, guys, I know this can be a bit much sometimes. It's a new weird section. But yeah, just ask me anything if you need to. All right, so let's look at number 2. Number 2 is telling us Bob does not get a 90 on the final. That's still telling us something about P. P says Bob gets a 90 on the final. 2 is saying Bob does not get a 90. So 2 is telling me that P is false. P is false, right? He did not get 90 on the final. So what does it tell us about the implication? If Bob gets 90 in the final, then Bob will pass. Well, let's just put our labels here so we know what's happening. P is false here. Q is still unknown. And we need P to be false or Q to be true. There's an or there, so one of them has to be met. P needs to be false, which is met already. P is false. Q needs to be true. That doesn't matter because as long as we meet one condition, the thing is true, right? Because let me just go back to the rule here. P false or Q true. It's an or between the two. So as long as one is met, it's enough to say true. And clearly here, the first one is met. P needs to be false, and we meet that immediately. Our P is false. So it's an undo button here. No. Yeah, so that's good enough to say the entire thing is true. Okay, let's go over all of them like this. What is 3 telling me? It's telling me Bob passes the class. That's telling me something about Q. So that tells me Q is true, right? Look above, Q says Bob will pass the class. 3 says Bob passes. So that's telling me that Q is true. So if Q is true, I'll do the same procedure again. Just follow the rules above. What am I doing here? It's restating the implication, okay? And we now know that Q is true. So if Q is true, does this follow anything above? I don't know if I should keep restating this. Let me do it one more time. The conditions we need are here in green. We need that to be false or that to be true. Now this doesn't seem to meet any of them, at least not the first one. Right, this is definitely not met. Our thing is true, but it needs to be false. Q, we don't know anything about Q here. So if Q changes, this whole thing could change. So we don't know enough to say anything. Not enough info. Okay. Maybe I should stop changing colors now. I'm wasting too much of time. Okay, 4 is Bob fails the class. So that's telling me Q is false. So Q is false. If Q is false, then again, I'll restate it here. It tells me something about Q. Q is false. According to our condition above, let me just circle this part here. According to that condition, do we meet any criteria here? Is P true? No, sorry. We need P to be false or Q to be true. Is P false? No. Is Q true? No, it's not. But still, we don't know anything about P, so can we say anything? I don't think so. Not enough info. Right? Yeah, that's correct. If P changes, the whole thing could change. So not enough information. Seems to be coming up a lot here. Did I miss something? Let me just check 3 again. 3 says P true.
Sorry to bother you. We do have some questions in the chat.
We do, okay. Let me
Yeah.
have a look. Thank you. Okay, yeah, and it's a weird section, so I expect some confusion.
Yeah, so it's a bit like confusing, yeah.
Okay, so the first part of the statement is always P, and the second part is always Q. And to be false, as he did not get 90, so he failed the class. Okay, so all valid questions. Let me look at 2. And now what did I just do? Okay. Can I just move this thing, please, somewhere? Okay, 2. Sorry. Yeah, so this does happen often. This is the problem with using English in these things. They're supposed to use mathematical statements. So the question was, shouldn't it be false? Was it? Go back. Yeah. New messages. So that's what you would think initially, right? You'd think it would be false because he does not. But it's if you try and understand this in terms of English language, and it gets a bit confusing. In the final.
So if I'm trying to understand this right, basically,
yeah,
both statements up top is like kind of true, right? So we need to basically falsify it to get this answer. Is that what we're trying to get?
Sorry, when you say both on top, you mean the original
yeah,
P
so
and
the
Q
original
right
one.
here?
Yeah. So they both like telling us this is true. Well, if he does get 90, that is a false if he gets a 90, and then the second one would always need to be true. So I'm just trying to get it that now we're trying to reverse the roles to make it false. So that top statement is true, and then we're just trying to make it like incorrect to get the answer. Yeah.
Okay, I can see why you'd think that, but no, it's actually simpler than that, right? Again, so I'm going to ask you guys to try to just reprogram your minds for a second and not try and think of this in terms of a sequence of events like how we would in English, because I get that. Okay, firstly, whether P and Q are true or false, we don't know, right? We're assuming we don't know that, and all of these points, 1 to 8, is telling us something about whether a particular one is true or a particular one is false, right? It's whether they are true or false, we don't know from the question. We have no idea. And based on whether the individual ones are true or false, which is given to us in 1 to 8, we have to then use the rules of the table to determine whether the entire thing is true or false, this entire thing here. All right, so you know what, guys, maybe let me stop there with this example. The one that uses maths is probably easier to understand. So maybe I'm going to start here, and then whatever I didn't finish here, you guys can try as homework. Okay, because this one is clearer, much clearer. So let's try that, right? I get this is difficult to do when we're not in person. It's not a nice thing, but this one should be better. So if I'm losing anybody here, let me know. Let me just get back to the chat for a second and see anything. 3 might, yeah, wouldn't 3 be true because Q is true? That's very possible. Oh, okay. If you return to the unknown, okay. All right, guys, yeah, I think you're right about 3. Let me just clarify that. But other than that, these other questions, let me try and finish this, then I'll get back to them, because possibly all of this will be cleared up by just looking at a simpler example. So 3 says Q is true. Yes, you're 100% right. Sorry about that. I knew something was wrong here. So this is enough to say true. Okay. But again, if you're not with me, it's okay. This will be clarified now in this example, I hope. So this example says decide which of the following statements are true and which are false. Briefly explain, not necessary. We just need to understand mathematically why it's so. We'll talk it through, right? Okay. So in a situation like this, we still need a P and a Q. We don't have to label them necessarily. Just know that the first statement is always P and the second one is always Q. Again, you can label them whatever you want. We're just choosing P and Q for convention's sake. So to determine whether the combined statement is true or false, we use the rule from the table, which I'll restate down here. The rule says the implication is true when P is false or Q is true. It also says or both, but that doesn't really help us. So these are the conditions. If we can meet one of these conditions or both of them, then it means the thing is true, right? So let's see if we can meet these conditions in example 1. Example 1, clearly P is false, right? 0 is not equal to 1. That's definitely false. And the Q statement is definitely true, right? So all we got to do is now determine whether what we have is consistent with the rule here. If it is, then we can say true. If it's not, we say false. So is this consistent? Let's see. Is P false? P is false, right? Our first one is clearly false, so we've met that. Is Q true? We've met both of these, actually. Both are met. So that's enough to say this entire thing is true. Okay. So I'm just going to do all of them because I know it's confusing. Catch everyone somewhere where they fall off or don't understand something. Let's hope. Let's see. So here, let's see, example 2, our P is definitely true. There's no doubt about that. We all agree that 1 is 1. Most horses have 4 legs. See, I'm always skeptical about things like this. Most horses, they say most, so I can say true. Hope I don't offend anybody by saying true here. So trues here. Now, does this meet any of the conditions from our rule on the right? Our rule on the right says P needs to be false. We don't meet that condition. It says Q needs to be true. We do meet that condition. And as long as we meet one of these conditions, because it's an or, as long as we meet one, it's good enough to say the entire thing is true. Okay. So the next one here, there's a lot of words here, but let's see what happens. If 8 is a prime number, so where's the statements here? The first one, 8 is a prime number, that's the statement. Then the 7,624th digit of pi is an 8. Okay, so I'm suspecting there's a reason they did this. 8 is a prime number. I think we can say that's false, right? 8 is not a prime number. The second condition, true or false, who knows? But probably we don't even need to know. Let's immediately take our first condition and go to the rules and see if that's enough. So P is false, we know that. P is false is the first condition, so we've met that. As long as we meet one, it's good enough to say the entire thing is true. So we don't have to even check the second thing, the second statement. We've met the first condition, that's good enough. Okay, and this last example. If the 6,624th digit of pi is an 8, again, we've established we don't know that. Of course, we can look it up, but it may not be necessary. Let's not jump ahead. The second part says then 2 plus 2 equals 4. And we know for a fact that is true. So is that enough to say something about this? According to our rules on the right, let me erase the previous thing. According to the rules on the right, 2 plus 2 is 4. The second statement is true, and that is consistent with the rule. So we've met a condition. Because we've met a condition, we can say true to this entire thing. Okay. All right, so hopefully, do you guys find this example more helpful than the first one? Just give me like a show of thumbs up or something so I know.
So I just want to ask, right? So if one statement is met, then it's automatically true.
Correct. That's 100% correct.
So if both of them are like not met, then it's false.
Yes, exactly.
Okay, now I'm understanding it. Yes.
Okay, perfect. I couldn't have said it better myself. Okay. And also note if we meet, if one condition is not met and we don't know something about the other, there's not enough information. We can't make a conclusion. Okay, all right. So you guys can go back to this one and try it. Again, remember all that these numbers are telling us is whether P is true or Q is false. In fact, let me fill that in for you guys. All this other nonsense here, let's take it out. We don't like it. We don't want it. This will make it like the example we just did. The example we just did, it's clear by looking at them whether something is true, something is false. Here it's not really clear, it's being told to us. So they're trying to make it clear. So anyway, the first one is telling us Bob gets a 90, so it's telling us P is true. This one is telling us P is false. Second one is saying Q is true, then it's saying Q is false. 90 and passes. So that's saying Q is true and true, because both happened. Fails, so this is saying Q is true and P is false. This is just covering all cases here. Then this one here is saying Q is false and P is true. And this, of course, should say both are false. Let's see. Does not get a 90 and fails. So this is saying Q is false and P is false. So knowing this, we can apply the rules and then determine whether the entire thing is true or false, just as we did in this new example. Hopefully that makes it a bit better. All right. Sorry, guys, I'm not online, so I can't give breaks in between and stuff. I have to just keep going. But again, if you're battling, just watch the video. That's okay. All right. Any questions before I move on, though? I'll pause for a second and interrupt me if you need to. It's okay.
Sorry, sir.
Yes.
Now, Alison, you go. Alison.
I'm still a little bit confused. So we only need to meet one of the conditions.
We only need to meet one. That's correct.
So what happens if they both turn out to be? So for number 3, what happens if 8 is the 7,000th digit of pi?
Then it doesn't matter. It probably is. I don't know, but let's assume it's true. If it is true, it doesn't change anything because P already is false. So we meet the first condition. Right?
But then number 4 is not correct because if it is true, then it's true and true, which means it's false.
True and true gives us false. I don't think so because number 4, Q is true is a condition and we've met a condition, right? So as long as you meet any condition, it's good enough to say true. So in this one, even if this were true, it doesn't change anything because we didn't meet the first condition. We have to meet one. Remember, we just need to meet one for it to be true. Okay,
I'm going to have to read up because I think that confused me even more.
Yeah, sorry. Sorry. Yeah, I know, guys, when I first started trying to learn this thing, which was like 3 years ago before I took the module, it takes some digesting to get the stuff. Not sinking in immediately, it's okay. It's all right. In fact, if we need to set up an extra revision session for this other than our normal, or if I need to just make an extra video question, we'll see what we can do.
I just want to ask something quickly. So
as bad, I hope.
Both is proven to be false, or if nothing is proven, then it's false.
Sorry, I'm struggling to hear. Say that again, please.
Okay. So if we can't prove anything that Q is true, Q is false, so no was met, then that means that the statement is false.
I think I heard you, and if I did hear you, then that's correct. Yeah. I'm hoping I heard you right, though.
I think you did, yes.
Okay. Do me a favor, if you're on the group, maybe just send a WhatsApp to me on the group, and I'll get to that as soon as I can. Or, yeah, WhatsApp is easier because the chat gets a bit of a nightmare to keep going back and forth.
Sorry, so I just want to ask, right?
Yes.
Okay, I know, like in an exam venue, we would never know what the 7,624th term is of pi. But I asked ChatGPT, and they saying it's like 6. The digit is 6.
Okay.
So therefore, like in the statement, it would be false. So then, what would we do for 3 then? But it would still actually be true because the one condition is met, is what you're saying.
Yeah, exactly. So yeah,
because then therefore it would make 4 the first statement. We can just assume that it's a false one, and then therefore 2, like the 2 plus 2 equals 4 is true. So therefore it's already met one condition. So we just automatically say it as true. So like even if we don't know it, we just state what we think it is, and then we get the mark like that, if I'm correct.
If you don't know it, yeah, so good question. If in an exam you don't know whether something is true or false, and if it's not obvious, first check if you need that piece of information. If you don't need it, then you don't have to say anything about it. Generally, if you end up guessing, it means you don't need it. So like here, you just, in exam, you could just write their dash. You don't have to say anything about it.
Okay, before you scroll down, that number 2, 1 plus 1 is true. That's the P statement.
Correct.
But you're looking for P as false.
Yes, that's correct. So that part is not met, right? The P is false is not met.
So then Q, most horses have 4 legs. Because it's true, the statement is true.
Yes, that's it.
All right. I get it, I think.
Yeah, we're getting there, definitely. So as long as you have one tick on the right here, so I got one cross and one tick. As long as I have one tick, I don't need anything else. The key is because there's an or here. So just one needs to be true. Okay. All right. So again, if I need to go back up, just let me know. It's okay. So now we look at direct proofs of implication. And guys, I'm going to emphasize this one here because every single year this comes out in almost every exam. In every version of the exams, this is always there in one form or the other. So I'm going to do this one in detail so we make sure if you don't know what's happening, just memorize it. It's okay. We need to know this one. So to prove an implication, again, implication is the form if P then Q. What we can do is assume P to be true and from it deduce Q. Right? So we assume P to be true, and from that assumption, we need to derive Q somehow. So here's an example of that. If, first statement, if two numbers A and B are even, then their sum A plus B is even. So if I start with two even numbers, A and B, then adding them together, I must also get an even number. That's what this is telling me. So how would I prove that? Well, first I assume P is true. P is the first part. So assume A and B are even numbers. So how would I express that? Well, this is the trick we need to know that makes our life easier. I can write A as 2 times, let's use J. And I can write B also as 2 times J, where J is just some integer. So I can put that restriction here. J is some integer. J is some integer. And let me explain why I did this. It seems weird and arbitrary, but think about it. No matter what I substitute for J, I will always get an even result, right? Actually, sorry, I can't use the letter J twice. It's usually not by convention. So let me just call this something else. Call it K. Doesn't matter. It just means the same thing, right? Let me show you what I mean. If I say J is an element of integers. Let me substitute any integer into this. Let's say, I don't know, -2 is an integer. If I plug -2 in here, the answer is -4. It's an even number. No matter what you substitute, you always get an even number. Even if I substitute, I don't know, 10 is an integer, sub 10 in for J, I will get 20, which is even. Okay, I'm always using, let's do one more. Suppose I use even an odd number, substitute an odd number like 3, answer is 6. So the result is always even if I use this form, 2J. 2 times any integer always gives me an even number. So that's the reason why we wrote it in this form. So that's how I sort of code the first statement. A and B are even. That's how I write A and B. Now can I prove that the sum of A and B are even? Yes, I can. If I write the sum A and B, can I prove they are even? Let me substitute the form that I just made up for them, which is 2J plus 2K. What happened there? I don't know. 2K. And from here, I can factorize a 2 out, pull a 2 out, and this just becomes J plus K. Right, now, will you guys agree with me that, okay, let me write it here at the bottom, a plus b is equal to 2j plus k. Just summarizing what I did above. Now, will you guys agree with me, firstly, that the form on the right is very similar to what I wrote on the left? It's 2 times some number. And we've shown on the left that 2 times some number, some integer, always gives you an even number. So by that reasoning, this here always gives me an even number as well. It's 2 times some integer, so it's always even. So that there's all we need. That's the proof. Yeah, it's quite a simple one. It always comes out, so maybe worth remembering this one. Okay, in fact, you might even be asked something like, if two numbers a and b are odd, then prove that there's some a and b's even. You know, they might just change things around a little bit like that. In fact, you guys can try that one if you want as well. And I'll give you a hint for that. If I change, okay, it's on video so you guys can see it. If I change even here to odd, everything else remains the same. And I want to prove this new statement. For that, I'll start you guys off. Just write a as 2j plus 1. That always gives you an odd number. Why is that? It's because 2j gives you something even. You add 1 to something even and you get something odd. So this always gives you an odd number, and b will 2k plus 1. Again, the restriction k is an element of integers. And then just try this. Add these two numbers up and see if you get something odd. Something even. That's the claim above. You add them up, you get something even. So try that at home when you get a chance. I only have 10 minutes, so I'm going to speed ahead a little bit. Okay, converse and contrapositive, again, just words we have to remember. The converse of a statement, if you see this word, it just means if you're given a statement, if P then Q, just flip it. If Q then P, right? That's the converse. Contrapositive means if you see a statement, if P then Q, you around and you negate each statement. So remember the symbol here with a dash with like a little drop is a negation. It's just the opposite of the original statement. Okay, and logical equivalence is also something we need to know. So the converse we say is not logically equivalent to the original. And that's important. It basically means if the original is true, then we cannot say that this is true. We can't say that. We don't know that. But the contrapositive, it works that way. If we say that the original is true, then the contrapositive is also true. So that is logically equivalent to the original. Okay, so that's all we need to know there. And let's see. Again, guys, a lot of things to memorize, unfortunately. This is just telling us that an if and only if statement can be rewritten in this way. Very complicated, unnecessary way to rewrite it, but you can do that. You can rewrite it in terms of implications separated with an and in between them. I guess we're doing this because we're working with implications very often. So if you're comfortable with that, you can rewrite and if and only if in terms of if then statements with an and in between. Okay. And again, this is stuff just to remember. If you this stuff to read, right? If you're told that P is necessary for Q, it basically means this implication of this form. If you're told P is sufficient for Q, it means this implication of this form. If something is necessary and sufficient, P is necessary and sufficient for Q, it means double-sided arrow. So if and only if. Yeah, so again, these are just things to remember. If you see these words in a paper, you need to know how to convert the words into the statement. Okay. Okay, so we have an example here, which we probably should do. Rewrite the following using the if and only if box above. That box is this one here. So can I make all visible together? Yes, I can. So I will watch a movie if and only if it rains. So I must rewrite that using this box here. I'm sure we can do that. So I will watch a movie is one statement if and only if it rains. Okay, that's worded in a very weird way. Yeah, okay, but it's fine. Let's just do it. I'll watch a movie if and only if it rains. So if I rewrite this, let's just call this P and call this Q. And this, what we have right here is a double-sided arrow. Because the double-sided arrow is I will watch a movie if and only if it rains. Now what we're told is we can rewrite this as, I'm just going to copy it from above, as the implication this way, and the implication that way. So you guys can rewrite the whole thing in words if you want to, but I'm just going to say it out so we can see. So this one here, the way we will say it is exactly as it is above. I will watch a movie if and only if it rains. The way we will say this is, God help me, let's see if I can do this one. Okay, we know what P is, we know what Q is. This is, if I watch a movie, then it rains, and if it rains, then I watch a movie. So apparently what I just said is completely the same as just saying it simply. I will watch a movie if and only if it rains. So I think this is where politicians learn how to speak, probably. So they can sound confusing by saying simple things. But yeah, again, that's just stuff to remember. Okay, a lot of new stuff here just being thrown at us. So I'm trying to keep it as reasonable as I can, guys, but unfortunately I have to just go through all these things. Universal and existential quantifiers. So this is now a way to write usually restrictions in maths, restrictions or rules or things to abide by. And the first one that we're looking at, it's just like a symbol which means a couple of words. If you see this symbol here that looks like a backwards E, how you read this is there exists. Right, that's helpful because the word exists is with an E, and this is like a backwards E, so it's helpful to remember it. And the one at the bottom called the this the existential quantifier. The universal quantifier looks like an upside down A, and this is read for all. And that's helpful because the word all is there, and it looks like upside down A, so we can kind of read that. Okay, so how do we actually read something? Well, this example up here will be read, there exists an X where X is less than 0. So it's just like learning math speak, basically. Just saying exactly what's there. There exists an X, and when you see the bracket, you can say where, or you can put a comma and pause. But usually we'll put a word to try and make an English sentence flow out of the maths. Right, so there exists an X where X is less than 0. The one at the bottom, what is this one? It was for all. So I'll say here for all X, X is greater than or equal to 0. Okay, again, just another way of speaking and saying these things. And now they're giving us a double trouble here. They're using these quantifiers and making a statement and asking us whether the statement is true or false. So firstly, can we read this thing? Let's see. For every X, there exists a Y where Y is less than X. That's how you would read that. I'll say that again. For every X, there exists a Y where Y is less than X. Okay, you could say for every or for all, doesn't matter. Let me say it with for all. For all X, there exists a Y where Y is less than X. Okay, and they're asking us whether this is true or false, and claiming already that the answer depends what our domain of discourse is. So that means whether we're looking at domain of discourse means whether we're looking at real numbers or integers or whatever, that tells us whether the statement is true or false. So let's start assuming we're looking at natural numbers, right? Just to recap, natural numbers are counting numbers. 1, 2, 3, 4. Now, is the statement true for that? Let's think. The statement is basically saying for any number x, there will always exist a y which is less than that x. So I don't think that's true for natural numbers. Because again, the statement is saying for any number, you can find a number less than that number. But for natural numbers, if my number is 1, I can't find a number less than that. So that's not true for natural numbers. Right? For whole numbers, is it true? Remember, whole numbers are just 0, 1, 2, 3. So for whole numbers, can I always find a number less than a number that I'm looking at? Right? for most of them it's true, but if I come down to 0, I can't do that. I can't find a number less than 0. So the statement is false for whole numbers. You can't always find a number less than any whole number. And again, you guys can check it for the rest, but you'll see for integers, this is true. Integers go from negative infinity to positive infinity. For integers, for any integer, you can always find something less than it. So the statement is true for integers. So it's false for that, false for that. For integers, it will be true. Okay, I should have wrote false instead of crosses here, but anyway, you guys get the picture. First two are false, last one is true. Okay, and this is actually important stuff as well, but again, I'm going to dedicate 2 sessions to go through all of the stuff. Set theory is, okay, this is all important stuff. Okay, let's do a little bit, let's do at least the intro today. So this is how we define a set. It's just an ordered collection of objects. So A, for example, is a set. Is there a question for me? Someone has a hand up. Need help?
Okay. Sorry, sir. Are you gonna share that learning unit with us so that as soon as we get to the second part of it, at least we have an idea when you go through the lecture next time?
Sure. Sorry, I already did that just before the lecture. So if you don't have access, please let me know and I'll check.
Okay.
All right. Thank you. Thanks for reminding me.
Sorry, sir. I don't mean to be like rude here, but
no problem.
Isn't this only used in medication and science and all of that? What does computer science have to do with such hard maths, if I may ask?
Yeah. So the stuff we just did, unfortunately, this does come up in computer science. I'm not sure about set theory, but this stuff here. So maybe I should tell you guys this so you can be a bit at ease. All the stuff here, if you guys have studied binary and logic gates, right? Logic gates clearly is a thing that comes up all the time in computer science because it tells you the way binary bits interact and the way you need to code things in computers or build computers and stuff like that. So logic gates are important. All this stuff here is just a weird analogy to logic gates, right? The way P and Q interact, all these weird things is just telling you how the structure of logic gates actually works. So I'll try and make that clear at some point because the module doesn't make that clear. But when you do end up studying logic gates, which you will see all of this stuff comes up again. Except that time they don't use English because using English is terrible. They just use binary, just zeros and ones as statements and interacting these things based on whether we want something to go through or not go through, stuff like that. So in that sense, you will see this again, but in a much more digestible way. Yeah.
I see. So that's why I'm guessing computer science has the highest drop rate, like the drop rate is so high.
Yeah, I guess so.
This is quite a brain twister, I'm not gonna lie.
Yeah. I mean, I teach it and I don't like it as well. I have to keep looking up the rules because it's so much to remember, you know. So yeah, sorry guys, I hate to be this guy, but if you're ever upset with me, just remember I just work here. I'm not trying to torture you guys. Okay, so maybe since it's been a day like this, we should probably stop here. Yeah, I don't want to fry everyone's brains too much. Okay, so again, guys, I'll be here for another 10 minutes or so if you have questions, any concerns you want to address. Otherwise, thanks for your attention, and I will see you guys next week. Have a good one. Take care.
Thanks, Shamik. Have we got our ask task due for next week? Was that what you posted?
No. No, we don't. That was just the lecture slides. I'll make an ICE task, which I'll give you after the next lecture.
Thank you.
Okay, you're welcome.
Sorry, sir. I just have a quick question. In regards to the assignment, the question that was repeated, I'm not sure. I don't know whether, like, what's the way forward with that one?
Yeah, so sorry. As I mentioned, we're still waiting for feedback with that. So for now, just
Okay.
answer the thing exactly as it is, and anything that comes up after that, I will sort it out. I'll make sure you guys don't lose marks for things that are not your fault. So just answer it as if everything is fine.
Okay.
All right, thanks.
Should we make just one last